Hey guys, this is Taylor here, and today we are solving the problem number 3621, which is number of integers pop count depth equal to k. And this is the problem is from biweekly contest 161, and this one is fourth problem of the contest. Okay, so we will just quickly read the problem, then we will understand in here what the problem is saying. So you are given two integers n and k for any positive integer x. Define the following sequence: p of 0 equal to x, p of I plus 1 equal to pop count of p of I for all I greater than 0, where pop count is number of set bits in the binary representation of that number. Okay, this sequence will eventually reach the value 1. The pop count depth of x is defined as the smallest integer d greater than 0 such that p of d equal to 1. Okay. For example, if x equal to 7, so there are three integers, three set bits in 7's binary representation. So sequence will become 7, then 3. Then there are two set bits in 3's representation. So it will be 2. Then it will eventually reach to 1. So pop count depth of 7 equal to 3. Okay, your task is to determine the number of integers in range 1 to n whose pop count depth is exactly equal to k. Return the number of such integers. Okay, so let's see what is given to us and what we need to solve. So we have given something like n equal to 7 and k equal to 2, I think. K equal to 2, okay. Now let's see what we need to find. So first understand what is pop count. So pop count is basically the number of set bits in that integer's binary representation. For example, let's consider 7. So 7's binary representation is 1, 1, 1. How many set bits? How many ones are there? There are 3 ones. So pop count value will be 3. Okay. So let's take one more example. Let's say 5. So 5, I think we can represent like this: 4, 0 and 1. Okay, so how many integers are there? How many set bits are there? Two set bits. So pop count of 5 will be equal to 2. Okay, so I hope this definition is clear to you. Now what we need to find. So we have given that um, if we start from 7, let's say like this. So how many integers are there? 3. So I will reach 3. Now how many binary numbers are in the how many set bits in the binary representation of 3? I think we can represent 3 like this: 1 and 1. So there are two set bits. So I will write 2 here. Then if we write 2, so there is only one set bit. So I can go to 1. As soon as I reach the 1, so I can stop. So I just need to count this: 1, 2, 3. So my depth is 3. So for 7, it will be fixed. So for any integer x, depth count to reach 1. Okay, it will be fixed every time. So depth is 3 here. So let's take one more example, maybe 5 here. So 5's representation is 101, which is 2, because there are two set bits here, and 2 having the binary representation of 10, it's having one set bit. So I will write 1 here. So can you quickly tell me what is the depth of 5? What is the depth? If you are saying 2, then yes, your answer is correct. So I hope this thing is clear to you. What is depth and what is pop count? And if these two things are clear, the question is understanding of question will be very easy. So what we need to find, we have given some integer, okay? Let's say 7 or some n, okay? Let's say 7. What we need to find? We need to go to 1 and check how much its depth, how much its depth is. So one's depth is always 0. That is given to us in question. So we'll say one depth is 0. I will ask what is 2's depth. So second 2 depth is its binary representation is 1, 0. So its depth is 1. I think I don't need to explain because we have discussed here. What is 3's depth? So I can see third I need 1 and 2. So its depth is 2. So similarly, I can 4, 5, 6, 7. I will calculate depth of each of the number till that number, okay, from 1 to 7. And I will check, is this equal to k? No. Is this equal to k? Yes. I will count plus equal to 1. Is this equal to k? Let's say here some random numbers. For example, let's say 3 2 4 2. Okay, so I will check what is the depth. Is it equal to k? No. Okay, rejected. Is this equal to k? Yes. So I will again do plus plus. Is this equal to k? No. Is this equal to k? Yes. So I will do again plus plus. This way, if this was our condition, so our count will become 3 and we can safely return 3. I hope question is clear to you now. So how we will approach to solve this problem. So let's see how what we'll be doing here is. So the brute force solution that comes to my mind is, so I can write some recursive function, so which will return me the pop count. And pop count, how it will work? I will write something like pop count, and it will take some integer. If n equal to 1, then it can return a 0 because I have already reached 1. I don't need to do anything. Otherwise, I will go to the binary representation of that number. Okay, and I will check the set bits, count of set bits, and whatever that count of set bit will give me, I can return 1 plus pop count of this count of set bits. Okay, so this way, because why I'm adding 1 here, because for converting 7 to 3, I used one depth, right? I used one depth. That's why I will add 1 here and I will call for this 3 now. I hope that this is clear to you. So this is our basically brute force approach, and in last we can calculate for each for I from 1 to n. We can call this, and if answer, we can declare answer equal to pop count of my I, and if answer equal to k, I can definitely increase my counter. I can define it here and I can return the counter. So this was a quick overview of brute force approach. I think you guys must have written it. If you don't know, if you have any doubts, you can comment down, we can discuss on it. So if we see the constraints here, so cover constraints go from 1 to 10 to the power 15. So 10 to the power 15 is, I think, huge number. If I write some very optimized logic, let's say uh, for like order of n time also, no, that will not gonna work. Okay, surely this thing is very clear to us, because 10 to the power 15 is very huge number. So one thing is clear, okay, I can't write a solution which works on this, even this. I need to think in little different way. So they have given something like this, and we have key range is very less. So this thing is somewhat it's hinting me towards DP. Okay, we'll come on that later. But this thing, when I see this thing first, na, I thought of DP. Okay, so we will see how we will reach to DP. But let's see for now. So how what is the intuition behind this problem? How we can solve this? So if I write very huge number, okay, if let's say if I write 10 to power 15 number, what that number? How many bits will be there in that number? I think it will be in the longs range, in the long range. So long range is 2 to power 64, right? And there are 64 bits in that long. I think it will be definitely less than this. Yeah, I think 10 to power 15 is something around 2 to power 50. It will be 50 bits. Okay, so I can definitely fit my answer in this range. This thing is clear to me, first thing. So if I write some my solution around this 64, so it can be either order of 64 or either order of 64 into 64. Something like this will definitely work. So I can think my solution in this way. So why I'm telling all these things to you, because next time any question comes like this, na, which having that much long length, 10 to the power 15 constraint and all. So how to approach problem? If you keep thinking of a solution which is order of n, that will not gonna work. That will not help you in solving the problem. So you need to think in terms of this order of 64 or order of bits. Let's see what we can do now. So before going into intuition, I want to reiterate on one thing. Okay, so I have written something here. You know what is this? This is binary representation of 10 to the power 15. Okay, so I can write something like this. It is binary representation of 10 to the power 15. If you carefully see here, how many bits are there? It's somewhere around 50 bits. Okay, so 50 bits are there total. And if I ask you how many set bits are there, so if I can count, it's 3, 4, 5, 6, 7, 8, 9, 10. So I'm not gonna count in it, but it will be definitely less than 50. For example, let's say there is 30 bit set. Okay, 30 bits are set. So, what will be my next number? What will be my next number? Can you guess it? If I am at 10 to the power 15, and if in the worst case, let's say worst case, okay, all bits are set, every bit is set. So, what will be my answer? My answer will be 50. Why this game? So, if you want to reiterate on it, I was here, all bits were set, and how many bits were there? It was 3 bits. So my next number was 3, right? I went to 7, then 3, then 2, then 1. This way I went. So here, what will be this number? This number will be how many set bits in this? How many set bits in 3? It will be this number. How many set bits in 2? It will be this number. So this way, if I do a observation, and if in a worst case, if all bits are set, so the worst number that I can get is 50 bit set. So my answer will definitely from that 10 to power 15 number, it will quickly jump to 50, right? Now you think that our problem is little easy. It becomes little easy, right? So let's see. Yes, it becomes really. So let's see how we will approach now. So we got some huge number in binary, but we can, if we calculate ki how we can reduce this problem to solve this using this. Okay. So we know one thing that whatever huge number I can have, it will definitely lie between 1 to 50 range, because if I count here, so let's say if I calculate the length of this binary representation, and I will take the exact binary representation here, so it's 50, right? That's why I'm saying, so it will definitely rise. So in the worst case, all bits will be set, so it will come 50. If some bits are not set, so I will get the answer in this range. So the intuition, the idea behind solving this problem is, if I calculate what will be my answer for this 1 to 50, 1 to 50, or let's say 1 to 64, for example. If I calculate answer, let's say any random number 60, what is the depth of 60? In how many depth did 60 can be reached to 1? If I calculate this, if I calculate till 64, okay, so my answer will be easy. So what I need to count then? So let's say we have some number x, okay, let's say that example x is, let's say 10 to the power 10, and in that x I have 40 bits set, okay. So my answer will 10 to the power 10 will eventually become 40 in the next step, right? And if I have calculated this number, that what is the set bits in this and what is the depth of this part, I think my answer is easy, right? My answer will be easy. So if let's say I take another example, let's say 10 to the power 12. And if I know that, for example, it's not a correct thing. So if I have, let's say there are 35 bits set. If I know this part, key, what is the depth of 35, then I think I can calculate the answer, right? So intuition behind solving this problem is this only. So what I will be doing is, so remember one thing, we don't need to calculate just for this number. We need to calculate from 1 to 10 to the power 12. So we have a little optimized our problem. So what we'll be doing is, we will be pre-computing the depth of 1 to 64, and that will help me quickly get the answer for any number. Now if you try to calculate for any number na, so from 1 to let's say 10 to power 12 I go, so I need to calculate for 1 to 64 is memoized. Okay, now from 65 I need to calculate, 66 I need to calculate till 10 to power 12. So I will not be going like this. I will be doing something in my binary representation only. Okay, so that part it will come from the digit DB. So we'll be checking that part as well. But now let's check how we'll be solving. So what I need to do here is, let's see. So let's say if I am at a very large number 10 to power 12, and if I can get 35 out of it, 35 bits are set, how many depth I have used? I have used k depth, right? I have used one depth. And how many depth is remaining here that I need to calculate? I think that is k minus 1, right? If this 35 can give me, if this 35 can reach 1 in k minus 1 step, then I would say, okay, this can be my answer. This 10 to power 12 can be my answer. Let's say if I use that 10 to power 12 minus 1, if I go like this, and if I say if I go in one depth and answer become 30, let's say, for example. So I will check whether this 30 can reach this one in k minus 1 step. If this can reach, then I can say that okay, this 10 to power 12 minus 1 can be a valid answer. It can increase my count. Okay, let's take one more easy example if you don't understand. So let's say we have some number, let's say 1000. Okay, and I'm considering that we have let's say 10 bit sets. Okay, so in one depth I can reach 10, right? And how many bits will be required to reach here? Let's try to calculate. So tens binary representation is, I think, 0 1 0 2 to power 1 2 3. Yes, I think this. So 1010 is tens representation. So how many set bits are there? I think two set bits are there. Okay, and how many set bits are in two? I think one. So what is the depth? 1 2 and 3. Our problem becomes really easy here. So what I calculated previously, that my tenth depth is 2. I know this thing. And to reach 10, how many depth I am requiring? Only 1. So if I calculate, if I sum up this 2 plus 1, this is becoming 3. And if my k was 3, then I can add it. Okay, yes, this can be my answer. If my k was, let's say, 4, so I was saying that okay, this is not satisfying condition. If my k was 2, then this is not satisfying. But my k is equal to 3. I have used one bit here, and if this 10 can reach this one in 2 depth, then I can say this is my valid answer. I hope you guys got it. It's pretty much clear that why we are using this k minus 1 logic. So what I need to find, my problem becomes really easy now. So what I will be doing, I will be getting some number which can be from 1 to, let's say, 10 to power 15. I will be calculating in one step how where I can go. Okay, in one step where I can go. And if that number lies between 1 to 10 to 1 to 64, I know one thing for sure, that this number will lie in this range only. That is we know for sure. So we will just pre-compute that for this number, what is the depth? Okay, what is the depth? And I know this depth is, I have calculated 1 to 64. I will be calculating depth in advance. I will be just quickly checking whether this depth is satisfied. If say yes, this depth is, let's say, 2 and here is 1 and this becoming 3. So I can quickly get my answer. Okay, yes, this number can satisfy. Now check n minus 1, check n minus 2, check n minus 3 till 1. We have to check, we have to calculate from 1 to n every time, right? So I think this part is clear to you. Now what we need to do, just to calculate from 1 to n, we can't go and iteratively and calculate this part for each time. What we'll be using, we'll be using digit DB. So let me bring one example and we'll discuss that how digit DB can help us. So before going into digit DB, let's first quickly write down what we have discussed so far. So first thing we discuss is, okay, what is depth? What is depth? So depth is in how many times my number can reach to 1, and how it will be reaching using pop count. Okay, so just to give you a quick example again, so 7's representation is 111. I reached here 3. Now 3's representation is 1 1. I can put 2 here. Now 2's representation 1 0, I can read. So this is 1 depth, 2 depth, 3 depth. So my answer will be 3. Okay. So this is basically the definition of depth. I think this is clear to you. Now let's quickly go to the second thing. So what I figured out is any number from 1 to 10 to power 15, which is my constraint. If I just apply one pop count, okay, if I call n with pop count function, I will get number in range 1 to 64. Okay, so ideally it is 1 to 50, but why we are considering 64? Because it's a standard long range. That's why we are saying 64 here. And otherwise it can be 50 also. If you say 50, that answer is also correct. Now, what is my second observation is, this is my first observation. Okay. Now, second observation is that if I can reach in range 1 to 64 in one depth. Okay. So that number, whatever number I reach, let's say I reach 12. So that number should reach in k minus 1 depth. That is my condition. If that number will reach in k minus 1 depth, then this number, whatever number I was calculating, let's say n, this number would be valid. Otherwise, it would not be valid. This is my observation, right? Now let's see. I think this much idea is sufficient to proceed now. Now, what we'll be doing? So we have to do something in bits, right? So let's say we have some bits like this. Let's say 1 0 1 1 0 1 1 0 1 1. Okay. So how many set bits are there? 1 2 3 4 5 6 7. Okay, so let's say this number is, let's say, some 4 5 7 9 8 4 2. This is some huge number. For example, I'm just taking random example. So let's say this number's binary representation is this. So I will just count 1 2 3 4 5 6 7. There are 7. So it will eventually reach to 7. Quickly it will jump from that huge number to 7 because there are only 7 set bits. Now, if let's say my k is equal to 4 and I have used 1, so just to reach from 7 to 1, if this 7 can reach in 3 steps, then my answer is valid. Otherwise, I will try for another number. I think, yes, it is clear. Okay, so what I will be doing here is I will count. I will be I will work in a smart way. What I will be doing? I know I have utilized one here. I have utilized one depth here, and I have remaining only k minus 1 depth. So can I figure out how many numbers? How many numbers are using k minus 1 depth? Then my problem becomes more easy, right? If I figure out that from range 1 to 64, as I have used one depth here, my remaining depth is k minus 1. So how many numbers are using k minus 1 depth? Let's say k 4, 7, 9. Only three numbers are using. Then these numbers are of my interest. Rest all numbers I will discard. I don't have any interest in them. Okay. So I will be working on these numbers only. Now I need to figure out how many numbers from 1 to, let's say, my this huge number n, how many numbers are reaching to any of these, either 4, either 7, either 9, because these are using k minus 1 depth, this is using k minus 1 depth, this is k using k minus 1 depth. Now how many numbers in this range can teach either this, either this, either this? I hope this part is clear. This part looks little tricky, but once you understand it carefully, if you don't understood it, you can comment down for your doubt. Otherwise, just rewatch the video again. Okay, so we have created our subset. So let's say our subset is like this at 4 7, and I'm only having this numbers which I am interested in, and I need to just calculate how many numbers are reaching here. Now I know one thing also. Okay, now my problem becomes really easy. You know why? Because I know I need to figure out the number in which only 4 bits are set. Okay, only 4 bits are set. I need to figure out a number in this range in which only 7 bits are set. Okay. I need to figure out a number in which only 9 bits are set. Okay. So I just need to Now, now I can solve if you have a strong permutation or combination logic. Now, you can solve it using that also. If you know digit DP, you can solve it using that also. Okay. So it's your choice. You can either use this, you can either use this. This will be, I think, little optimized version. In this, we have to iterate. We have to do recursion as well. So we'll be using this for this lecture and we'll be using recursion. Okay. So you understand, right? So my problem become really easy now. Now I just need to figure out from this range how many numbers are there where only 4 bits are set, where only 7 bits are set, where only 9 bits are set. If I figure out that number, that numbers count, I don't need to figure out that exact number. I need to figure out how many numbers are there which can eventually reach here. So if I have count in hand, I can directly return that count. Yes, yellow. This is your answer. Okay. So how will you figure it out? So I know one thing that uh, how many combinations I have. So let's say my number is this, no? This 4799, that big number. So let's say that representation is something like this. Okay. So how many bits I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say 11. Okay. So what I will be doing is I will be trying out all combinations. Okay, which should be less than this. One condition is there. One condition is very important, that whatever number I try to reach out there, that number should be less than this, because I need to figure out only less than n, 1 to n, right? So I will be trying all combinations and I will be checking like how many combinations can reach eventually either 4, either 7, either 9. Okay. So let's say for just for an example, if I write something like it's 11 numbers, right? So let 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This will be answer or not? Tell me, this will be a valid answer or not? Yes, this will be a valid answer. Or what I can do? 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1. This will be my answer or not? Yes, this will be my answer. Let's try for 7. Okay. So 1, 2, 3, 4, 5, 6, 7. So this will be my valid answer. This can be my valid answer. I just need to figure out how many combinations are there. So tell me now, is this problem hard? Is this problem really hard? No, it's not. If you know digit DP, or either if you know permutation combination very well, you can solve it problem. So digit DP is we will be using digit DP, and digit DP is having its own structure, its own format. Like we have binary search, right? We follow some certain structure. We have segment trees. We follow certain structures. So in this DGTP also we follow certain structure. So what is that structure? Let's quickly see by an example. 14. What is 14's binary representation? 1110. Okay. 1110. I will be taking this as example. Now what I will be doing is I will try to figure out all the numbers which are less than this. So I have four places to cover. Now I can either use 0 or I can use 1 in this place, right? If I place 1 here, okay. Now if I place 1 here, now I have a restriction here. What is the restriction? I can't put triple one here, because if I put triple one here in front of this, this number will become larger than this. Okay. So that's why I'm having certain restrictions. When I'm using same numbers like this, and I am in restriction mode, then I will be in restriction, that I can't use triple one here. Okay, so let's try all the combination. Okay, so I'm again writing here 110. I will be trying to write. So I will be doing here that okay, I will write one here and rest combinations I will find in future. And if I write 0 here in this place, so there is no restriction, right? So I can place 1 here, 0 here, whatever I can place, that number will be definitely less than this 14, right? So one thing I know, that if I am in restriction mode, initially I will be in restriction mode. This is concept of digit DP. We can't explore all whole digit DP here, but I'm just giving you idea how digit DP works. So if we have certain number like this, and if we have one here, we are in restriction mode, and if we use that exact number, we can't we will still be in restriction mode. Otherwise, if we don't use that number, we use less number less than that, then we will be in no restriction. Now I can use either one here, either 0, either 1, yeah, फिर all ones, yeah, 0 1 1. That will not be an issue. Okay. Now here what can I do? I am in restriction mode. This is 1. What I can do? Either I can fill 0 or 1 here. If I fill 0, okay, then this is was 1. I filled 0. So I am not no longer in the restriction mode. If I use 1 here, I1 is in restriction mode. I use the exact same number. So I am still in restriction mode. This is restriction mode, restriction mode, restriction mode. Okay. Now let's say our third bit is 1. Okay. I can again use 0 or 1 here. If I use something like 0, so my restriction mode is not there. Okay. And if I use again still 1, 1, 1, and this place is empty, so again I am in restriction mode. So I hope we are getting what we are doing. So okay, so I hope this part is clear to you. Ki why we are using digit what exact thing we are using in digit We are just trying to figure out how many combinations are there, which can either reach to 4 digits 1, 7 digits 1, 9 digits 1. Why we are doing this? Because we know our k minus 1 is lying in this integers. Okay, so if you have any doubts in this part, in any of this part, just let me know. We can discuss this in the comment section. You please feel free to put your comments. Okay. Okay, so we'll try to write pseudocode and we will check how we will be implementing all this in. So my first task is figure out all depth from 1 to 64. Second task is create subset uh, which having depth k minus 1. And third task is apply digit dp to find all number of possibilities. That's it. Okay. Now let's quickly see how we'll be figuring out what is the depth of any of this number. Okay. So for this, I will be just quickly writing off a pseudocode. So I will be iterating for I from 0 to 64. Okay, let's precisely it should be 1. We can use I think from 2 to 64 better. Why? Because one's depth count, I know it's already one depth count is 0. Okay, so just to figure out what is a depth count of 2, I will be using some dictionary or some hash map or some array so that I can store the value. So for now I'm using something kind of hash map. Okay, you can use array as well, that's not a problem. So I will be calculating the binary of this binary of I. Let's say it's something like x. I will be counting number of ones in x, then uh, that number, that number will be definitely less than that. So if I'm, let's say in this range, I'm in 10, and if I calculate the number of ones, so number of ones in max case, it will be double one, double one. So 10 is having only 4 digits. Okay. So if I calculate the binary of 10, so it will be 1010. Okay. How many set bits are there? It will be 2. In the worst case, it can be double one, so 4. So my answer is definitely less than this number. And for that less number, I am having answer that what is the depth of that number. So I can quickly get that depth. So my depth of current number, let's say I, will be equal to set bits. Okay, this set bits. So 1 plus my set bits. If you have doubt in this part, now this part is something like DP part. Okay, so if you have any doubts in this, just comment down. We can discuss this part in detail as well. No issue. So if we calculate like this, so we have one thing for sorted. Okay, I have ready. My depths are ready. Now I have to figure out how many depths are having k minus 1. So I can either use it here while calculating. I can calculate. Otherwise, I can iterate over this dictionary. And what I can do for uh, so key comma value in d dot items. Okay. So this is something like a Python pseudocode, but what we'll be doing, we'll be treating over the key and value. So key will be basically my the number, and value will be what is the depth of it. If value equal to k minus 1, then I can store key in set or any data structure, an array or anything. Okay. Now if I know this thing is done. Now I just need to apply digit TP here. So for digit TP we have a template, and that template is little lengthy to write here. So we'll be understanding that in the code itself. Okay. So let's move on to the code. See what we can do here. Okay, I can remove this. So one thing also, I will be calculating this, but okay, this part in my I'll be writing it outside of function. Why? Because this part I can keep handy every time. I don't need to calculate this part 1 to 64 every time, because this part was always same. It will be always same for any given constraint, any given constraint for any input. So let's quickly calculate it. So d of 1 will be 0 initially. Now for I in range 2 to 64, so to go to 64 I will have to write 65 here. Now let me put it on charger. Yeah, so uh, how I will be calculating it. I need to find the set bits, so I can write some functions here. Count set bits of n number, and how I'll be calculating binary of that number, and return binary dot count 1. Okay, so this way I can easily calculate okay, how many set bits are there. You can have your C++, Java, JavaScript implementation will be in description, so please follow me by checking that code as well. So set bits will be count set bits of I. Now what I need to do, d of I, or I can say a dp here as well, that will not be a problem. dp1 I should say here. dp of I, dp1 of I will be equal to 1 plus why 1, because just to go to this set bit I am using one operation, and how many operation will this set bit will use, that will be already calculated in this dp. So dp1 of set bits. Okay, so this way I will be having this thing handy from 1 to 64. If you print this, let's print it and see what is this dp1. If I print, let's see what is this. See, so 1 is having depth of 0, 2 is having 1, 3 is 2, 4 is 1, 5 is 2, 7 is 3. For 7 we calculated, right? It's 3. For 3 we calculated is 2. So it's correct, okay? So we calculated till 64. Now let's see how will be. So what's our second task? Second task is create a subset which having depth k minus 1. That is very easy. You guys can do it very quickly. So subset, I can create a set, I can create a list, anything. Okay. So for key comma value and dp1 dot items, if value equal to k minus 1, my subset, please add it. Subset dot add. Please add the key. Super. Now I will be copy pasting the digit TP code here, and we'll be understanding that here itself. Okay, so I have pasted my DGTP code here. Now what we are doing here, let's see. So I have written till here. My subset is having all the numbers which can reach to 1 in k minus 1 steps. Now, so what I need to do, I need to create a binary representation of my given number. Why? Because what we were doing here, what we were doing, so if I was given 1010, I can't go beyond this. I can only use 4 bits, right? I can't use fifth bit. That's why I am calculating the binary representation of it, and this will help me. So what I will be doing in digit table, if index is reaching that length, if index reach the fifth length, like I will be exploring combinations, so how many ones, how many zeros I can have, so that I can have only two ones. if I reach to use the fifth index, then I will use stop. You need to stop, right? So what I'll be doing here is, so binary number here. Now I can write something like dp. Okay, that is fine. I'm calculating a dp table of 65 into 65 into 2. Why so? Because I'm using here index. Index will be ranging from inverse case 0 to 64 ones. So how many ones I can have? I can have 0, 1, 2, 1, 3, 1, 4, 1, or either all bit sets, right? So in that case, I can have a 64 bit set. That's why I'm using this. And this tight is nothing but we discussed here, right? So we have a limitation. We were in restriction mode or not. Here we were in restriction mode. So tight will be 1. Restriction mode is not. So a tight will be 0. Here we were in restriction mode. So tight will be 1. Here there is no restriction. So tight will be 0. So this is like this. Now this is my base condition. So if I reach till end, if I reach the last index, and so that I need to check if my ones is in subset. Okay, ones is in subset means number of ones, count of one is in subset or not. So if my subset, let's say, contain 479, where it went, I think here, yes. So if my subset either contain four digit set or 7-bit set or 9-bit set, if any of these condition exists, then I can return 1. Otherwise, this will not be my answer. So I can return a 0. Super. Now, DP syntax, right? So if DP value is not present, if DP value is present, I can just take it. Otherwise, I need to set my new limit, right? So can I use, so limit will be basically, can I use 0 here or 1 here? That is my condition. So if I'm say here, okay, if let's say I went here. Now in this case, I could either use 0, either use 1. There was no restrictions. So that is the condition here. If tight is equal to 1, so if that means here tight is 0. If tight is 0, I can go beyond 0. So beyond 0 is nothing but just a 1 integer. So I can use either 0, either 1. So my limit is 1. Okay, limit is 1 means I'm iterating. So 0, then 1. That's why here is the iteration. So my limit is 1 here. If my type is 1, then what I am checking? If my type is 1, and so let's say here I was having 1, but let's say here I was having 0, right? So for this I was having 1, 1, 1, and 0. So let's say these bits are set. Okay, these bits are set 1, 1, 1, and I'm still in type position. Can I use 1 here? No, I can't, because if I use 1 here, it will be greater than this 1, 1, 0. So I can't use 1 here. I can't use 1 here. So my limit is 0 only here, right? And if this place I'm having 1, then I can use 0 or 1, right? Because I'm using less number than this. If I'm having some numbers like this, and I'm in this position, okay, 1, 1, 1, and I need to determine this bit. So can I use 1 here? Yes, I can use, because that will be less than or equal to this number. Yes, that's right. So if binary index is 1, then I can use limit 1, otherwise I can have a limit 0. And so what I'll be doing is, here I'm counting the numbers. So I need to calculate new type, right? So how I'll be calculating? If I was in restriction mode, that means type is 1, and I'm using a limit. So if I was in restriction mode, let's say here I was in restriction mode, and I'm again using same digit. I'm again using same digit, then I'm again in restriction mode. Otherwise, I will not. So that's what. So if I am in tight and I am using the limit, then I'm in restriction mode. Otherwise, I will be not. Now, next thing. So I will be just I will be just trying to figure out the next index using this. And I will be just appending how many ones I'm used here. I have used D number of ones. So D was 0, then 1. Okay. And a new type I will pass here, and binary number is just the static thing in this function. After calculating all this thing, I will be storing this in my DP and returning the answer. So I hope this problem is little clear to you. Let's try to see. Okay, yes, it is working fine. Now let's try to submit this and see whether it is working fine or not. You can see, right, how many approaches I tried. So I tried brute force, then I little optimize it, little optimize, then I came up to this. Okay, fine. So let's try to submit the code and see whether it is working fine or not. Wrong answer, superb. Okay, yes, this is this condition we forgot to add. I think so. If k is equal to 0, then my answer will be always 1, right? Yes. So we need to add one condition here. Equal to 0. Oh my, I can directly return 1 here. Okay, so we have added this condition. Now what why this condition exists is basically if my k is 0, that means I'm trying to figure out how many integers are there which are having 0 depth count. And I know I printed this, right? I printed this dp. If I print this dp and see how many numbers are there which are having 0 depth count, dp1 it should be, I can see only one number is there, which is 1. Otherwise, you can see who all numbers are there which are having depth count greater than 1. So if k is equal to 0, I can directly return 1. There will be always one number. Otherwise, I can try to calculate it. Okay, let's try to submit and see whether it is working fine or not. Yeah, it is working fine. So I hope I am able to explain you this tough problem, and if I did, please make sure you subscribe the channel and like the video, because this topic, complex topics takes a lot of efforts. So thank you very much guys for watching this video, and we'll meet the next one.